All right, let's think about how we can categorize and divide this problem into smaller problems. In fact, we can think of it as, let's say we have a sequence of numbers like this, and we divide this array into half. And we can divide this big problem into 3 cases. And the first case is the maximum subsum is in the left half, or the maximum subsum is in the right half. So that is the first and second cases. And the third case is the maximum subsum begins in the left half, so it starts from here, somewhere here, and ends in the right half, so here. So maximum subsum is located in this way. So these are 3 cases. And when we divide this big problem into small cases, there are 3 cases like this. And when you first see this approach, you might be wondering, this is quite simple, however, somewhat weird. However, you are going to see this approach, this kind of approach, more than several times towards the end of this course, okay? So you need to become familiar with this kind of approach. And now let's implement this recursive version together. So we implemented a naive solution, and we improved it by optimizing this for loop. And what we are going to do now is implementing using recursion. All right. So here I'm going to define this function as def max sum recursive. And our function needs to receive different parameters than this one. Because we want to use recursion, we need to define or design our function in a somewhat different way. So here we are going to receive our input array as well. However, what we are going to do is receive also a left index and the right index. So we only care about the numbers between left index and the right index. So when we do this, we actually want to use this function. What we are going to do is max subsum recursive driver. And this function only accepts the input array. And what we are going to do is, if the length is larger than 0, then we are going to call max subsum recursive A0 len A minus 1. So in the first case, we are checking all the numbers from the start to the end. However, this function cares only about the numbers between the left index and the right index given. All right. If the length of this array if this array does not contain any element, then we just need to return 0. All right. So this is how we are going to use this function. And let's implement this one. So what is the base case? The base case is when the left index equals to the right index. So this is our base case. So in our base case, we need to check another thing. If this number is larger than 0, then we're going to return this number. However, if this number is negative, then we are going to return 0, because we are not going to add this negative number. All right, so that is our base case. So here, we're going to divide our problem into smaller ones. So this is our body. And I told you that there are three cases. That the first case is the maximum subsum is on the left part, and the second case is the maximum subsum is on the right part. So we're going to implement those cases first. And to do that, we first need to define or find the standard index. The standard index is simply sum left and right indices and divide it by 2. And the maximum subsum on the left part is just by calling this function on the left part. So we are going to pass the same a, and we are going to check the left half. So this is going to be our first case. So this is our first case. And what was our second case? The maximum subsum is on the right side, right? Then we're going to call center plus 1 to right. So this is our second case, okay? So implementing the first and second cases are quite easy. We just call our recursive function in this way. And from now on, we're going to implement our third case. And to implement our third case, we need to define some variables to keep track of the maximum subsum. We're going to define some numbers like this: max border sum left, max border sum right. And these two numbers are initiated as 0. And left border sum, right border sum. And what we are going to do is we're going to iterate I So what we are going to do is, let's say, this kind of array. And this 6 or 5 is going to be our center. And what we are going to do is move to the left one by one. So we start from center and move towards the left boundary. In the first case, the boundary is 0 anyway. And so the idea is we start from the center and move towards the left part one by one and check if this sum becomes larger and larger. All right, so that's what this is doing. So we start from center and goes towards left part by decrementing I minus 1. And our left border sum is just adding the number at that position. All right. And if this left border sum is larger than the maximum border sum left, then we are going to update this maximum border sum left with the current left border sum. All right. And what we are going to do next is do the same thing on the right half side. So in this case, we change our I from center plus 1 to right plus 1. So we start from center and move to the right side one by one. And we are basically doing the same thing. Right border sum plus AI. And if right border sum is larger than max border sum right, that we are keeping track of, then we are updating this number with the current right order sum, like this. Okay, so this is our third case. So the third case is going to be max order sum right plus max order sum left. So this is our third case. And what we are going to return is maximum of among these three numbers. So max sum left and max sum right and max sum center. So among these three numbers, we're going to return the maximum one. All right, so this is the recursive implementation of subsum, finding the maximum subsum. All right. So are there any questions about this implementation? All right, and let's compare these three solutions. So this is some test code that is going to compare the subsum. So algorithm 1 takes 36 microseconds, and algorithm 2 takes 16 microseconds when n is 10. And our recursive version takes longer time when n is 10. However, when n becomes 100, the third solution, our recursive version, becomes faster. I told you about this, right? Because recursion entails function call. Sometimes it becomes slower when n is small. However, when n becomes 1000, then the naive solution becomes very, very slow. However, the second one, our faster version, is much faster than the first one. And our recursive version is even faster than the faster version. All right. So this demonstrates that efficient algorithms are very important. We can use our resources very efficiently. All right. So let's analyze our recursive version together. How are we going to analyze our recursive function? The key insight here is that it takes n over 2 plus n over 2, which is n additions, to compute the third case. Let's see what this means. So here we're starting from the center and moves toward left part with one step. And we start from center, move towards right with step size of 1. So these two for loop in total takes only n additions. Can everybody understand this part? And to compute these two cases, we are dividing our sequence into half, the left half and right half. All right. So if we say the total number of computations required for this algorithm or this function, let's say that is Tn. And if n is 1, then it takes only 0 computation because we just return that number. Otherwise, we are going to divide our sequence into left half or right half and call our maximum subsum recursive function here and here. So that corresponds to these parts. So this one is first and second cases, and this one corresponds to the third case. All right. And how are we going to solve this recursive equation? So this is basically this one. To solve this recurrence equation, it takes some discrete mathematics. Let's just claim that when we input 2 to the power of k, then it becomes k times 2 to the power of k. And we are going to prove that this one holds for every possible input. So let's do that. Can you prove this recurrence equation becomes this one using mathematical induction? Think about it on your own. I'll give you 2 minutes. And Seungjae asked this question. When we were talking about recursive implementation, I implemented 2 functions. The first one was, so I'll explain this part. The first one was our recursive version. However, this one receives left index and right index. So we cannot just pass our input array into this function. So we just need to make another function to deal with the first case, or just receive the input array, because the users do not know how to use this function. Okay, so when you think about other functions, they just receive the input array. However, this one looks different. Okay, so for users, we are going to just accept the input array, and we are going to pass the first elements index and the last elements index. Then this function takes care about the elements between these 2 numbers. So for the first case, we need to take care about all the numbers inside this array. So that's why we are passing 0 and len a minus 1. Does this answer your question, Seungjae? All right. Try to prove this by mathematical induction.